Mass, weight, and elevators. Mass and weight are not the same thing. Mass is a measure of inertia. It comes from all the atoms that make up an object. It's measured in kilograms, and it's the same no matter where the object in the universe that the object is. In other words, mass is intrinsic to the object. If we take you and we move you to Timbuktu, you have the same mass. And if we move you to the top of Mount Everest, you have the same mass. And if we move you all the way to the moon, or out to Alpha Centauri, or to the distant reaches of the universe, your mass would be the same because you would have the same number of atoms and they'd have the same amount of inertia tied up in them. Weight, on the other hand, is a gravitational force on an object due to a nearby astronomical body. It varies from place to place because it's an interaction. It's not intrinsic, it's extrinsic. It's the force on an object, not a property of that object. So if we take you and we move you to the top of Mount Everest, your weight would look more or less the same. But if we move you to the moon, it'd be 1/6 as much. And if we move you to Alpha Centauri or the deepest regions of the universe, it would depend on what the local gravitational constant is there. And that would depend on the other object you were near. So weight is not itself part of your body. When we say you have your weight, it really means that between you and the Earth there is a certain weight. The weight of an object of mass m, which is near the surface of the Earth, is simply m times g. We've used this a couple of times in class, and we might as well emphasize it again, that F sub g is m times g. So what is the weight in newtons of a 65 kilogram person? We would say Fg is m times g, which is 65 kilograms times 9.8 meters per second squared, or 637 newtons. An important fact to remember, you don't ever feel your own weight. Instead, you feel the contact forces that keep you from accelerating at g. For example, your feet are pushing on the floor and have biological pressure sensors in your skin that sense the floor pushing back. But because your body can be fooled, we say that you feel not your weight, but your apparent weight, which can be more or less than your weight, depending on the circumstances. In other words, your apparent weight doesn't have anything necessarily to do with your actual weight. Consider Alice, whose mass is 62 kilograms. That means her weight near the surface of the Earth would be 610 newtons. Alice is currently standing on a bathroom scale, and scales read the normal forces exerted on them. What do scales read? How hard you are pushing on them. What does the scale read when Alice is standing on it? Well, we might do a really quick free body diagram. This is a little bit overkill, but we might do this and say, oh, well, there's an Fg downward on her, and there's an Fn upward. And we know that Fn minus Fg has to be ma, which is 0. So this says that Fn equals Fg equals 610 newtons. Notice that otherwise noted in a physics class, scales read in newtons, not kilograms. The ability to say it's kilograms is an assumption that we're going to come back to that is not necessarily true in a physical situation. Anyway, this was a trick question. Alice is actually in a rocket ship which is accelerating away from the Earth at 30 meters per second squared. What is the reading on the scale now? Remember, the scales read the normal forces that they exert, that her mass is 62 kilograms, making her weight 610 newtons. And for this problem, we'll assume the rocket ship has just been launched, and thus is still, quote, near the Earth, and g is still 9.8 meters per second square. Take a second to figure out what the scale would read now. We would have the same free body diagram, and in fact we'd have the same equation that had been written, except this time I'm not going to casually assert that a is 0. So I'm going to say that the normal force is her weight plus her mass times the acceleration. This ends up meaning that she has 2470 newtons. Her weight, according to the scale, is 4 times her actual weight. Of course, it's not the rocket that's important, it's the fact that Alice is accelerating upward. We therefore often see these problems given as elevator problems, since the elevator can provide either an upward or downward acceleration via the normal forces exerted by the floor. This is as opposed to rockets, where we don't usually think about them thrusting downward towards the Earth or something like that. Alright, Bob mass is 81 kilograms. He's in an elevator which is currently accelerating downward at 4 meters per second squared. What is his apparent weight? Same kind of free body diagram. Here is Fg. It's being held out by the floor. There is a downward acceleration, and we know that Fn minus Fg is going to be m times that acceleration, but we need to respect its direction. Since the acceleration points in the same direction as gravity, then they have to have the same signs. If we grind this over, we'll see Fn is Fg minus Ma. And of course, Fg is just mg, so this is mg minus Ma, which I might factor as m times g minus a. And by throwing in numbers, we get 81 kilograms times 9.8 meters per second squared minus 4 meters per second squared, which turns out to be 470 newtons. Considerably less than his actual weight of almost 810. Charlene is in an elevator and is currently feeling as if she weighs 67% of her usual weight. What must be true of the elevator? Well, in this case, since she weighs less, so the normal force is less than it would be if she were at rest, it means she is in some sense falling. The floor is not completely counteracting gravity, so she must be accelerating downward. We have here graphically, we might say, draw a free body diagram. We know that there's the weight downward, and we know that what she feels is only 2/3 that. So we see that the net force must be pointing that way. From our earlier work with Alice, we could find an expression for the apparent weight of an object undergoing an upward acceleration as that the apparent weight, Fap, is the actual weight plus ma. Right? That the upward acceleration means we add in a correction term which represents that. And it turns out that this will also work for an object going downward acceleration if we include the acceleration as negative, the way we would expect. Someone unaware of being in an elevator, or someone just stubborn about these things, might insist the scale does read their weight. In that case, they'll say there is an apparent freefall acceleration g apparent, causing that apparent weight. In other words, they'll say the scale reads my weight, and my weight is mg, so therefore the scale must read mg. And then they'd say, well, if this is m times g plus a, then they would solve this to get the actual apparent, or to get the apparent freefall constant, as g plus the upward acceleration. And again, if the acceleration were downward instead, then we put an a as a negative number. For such people, all physics experiments would proceed exactly as we expect. They would get parabolic arcs for things they threw, they could do timing experiments and so on. Everything would be the same, except they would use this different value of g. So if they were in an elevator accelerating upward, they would see g as stronger. But everything would respect that. They would look the same as if g were that bigger number. In fact, if the elevator's walls were closed, then while the acceleration was going on, they would be unable to detect that they were in an elevator. Instead, they could say they had a uniform gravitational field of increased strength. All right, Fergus is standing in an elevator minding his own business when, all of a sudden, the cable snaps. What is his apparent weight as the elevator free falls towards the ground? Well, remember that, g apparent is g plus a. But in this case, the a is g downward. And so we end up with that the effective or the apparent weight is, the apparent freefall constant is 0. So the apparent weight, which is just the m times that, is also 0. Fergus would not feel any weight. He would think he was floating. If he let go of a textbook next to him, that would fall towards the Earth at 9.8 meters per second squared. But he's falling towards the Earth at 9.8 meters per second squared. So he would see it as floating next to him. He would think that he is weightless and that it is weightless and that things just float. Of course, this ends badly for him at the bottom of this arc if we're not careful, but during this time, he would think that he was in a weightless environment. Whenever an object's apparent weight is 0 newtons, it is said to be weightless. Notice that this is a misnomer. An object will only have a true weight of 0 newtons when it is very, very distant from all other objects. Otherwise, there'll be some gravitational attraction and there'll be some weight. By this definition, all objects in actual free fall are weightless. This includes places like the International Space Station, which orbits the Earth under the influence of the Earth's gravity only. Everything in the International Space Station is quote-unquote falling towards the Earth at the same rate, so things seem not to be falling at all. Now, because every object exerts gravity on every other object, NASA has taken to avoiding the term weightless and has started using something called microgravity instead. Not important, but they don't really like the term weightless anymore. In years past, NASA has operated modified aircraft that follow a parabolic trajectory to simulate weightlessness. Using its engines to counteract drag precisely, the aircraft provides about 25 seconds of free fall during each 65-second parabola. Due to the effect of weightlessness on human human physiology, these aircraft often bore the nickname Vomit Comet, because people would get physically ill while trying to do this.